In this part, we learn properties induced by CNN and compare this property with FCN. The properties are sparse interaction or sparse connectivity, parameter sharing, and equivariance to translation. Sparse interaction, sparse connectivity, or sparse weight has a similar meaning and concept, and it means a small kernel detect meaningful features such as edges. This is a property by CNN. It reduces memory footprint and also computational cost. Assume we have input size of 3 in 3 and filter size of 2. We use the neuron-wise representation of the CNN as you can see here, and when we move the filter into the first spatial location of our input, we can have the first output of our feature map. As you can see here, in order to get the first entry, we have 4 connections. Similarly, for the second entry of our feature map, again, we have another 4 connection. Now, in total, we have 8 connections so far. And in continue, like now we have 12 connections for the third entry. And at the end, for the whole feature map, now we have 12 connections in total. However, in dense layer, these numbers are different. Assume you would like to replicate architecture with ResNet. Now we have non-layer, non-neuron as input, and then for the second layer also we have 4 neurons. Each input neuron is connected with each hidden layer for the second layer. Therefore, in total, we have 36 connections. What does it mean? It means indeed for CNN we have receptive field of 4 neurons, while this number for the dense layer is 9 neurons. Indeed, in CNN we do local search for feature, but in dense layer we do global search because each neuron connected to the neuron for the next layer. Well, if I want to say in an example is like when we process images, it's more likely a specific feature occur at a specific location of our input. For example, if we have a face as an input where the eyes are in a specific location, CNN assume, okay, this feature occur in a specific location, therefore it does local search. However, for the DenseNet, it's not like this, and it thinks every actually pixel has an influence for the location of eye. Therefore, it does the global search. Another property is parameter sharing. Parameter sharing is used to control the number of parameter or weight used in CNN. In previous lecture, we saw like each weight in dense layer is used exactly once. However, in CNN, we assume that if the one feature detector is useful to compute one spatial location, then it can be used several times and it can be used to compute different spatial positions. And as we share parameter across the CNN, it reduces the number of parameters to be learned and also it reduces computational needs. Okay, in this example, I draw your attention on the filter. Okay, in particular, consider the first actually filter that we have here with our filter size is 2. Again, our input size is 3 in 3. And by moving the filter into a first spatial location and in order to get the entry of the feature map, we can see, okay, we use for the first entry, we use 1 time the first weight. And if we continue to the next location, we can see, okay, we use it another time as well and go on. Then in total, we use 1 weight 4 times. And in total, we use 4 weights, which means we only need to learn and tune these 4 weights during the training procedure. Now, the question is how many weights does a corresponding DenseNet use? Yeah, as I mentioned earlier, each weight we use it only one time. Therefore, in total, we have 36 weights to be or parameter needs to be learned during the training procedure for the dance. And why is that good? Because first of all, we have the less parameter, therefore it needs the less memory requirement, and also we will have the fast runtime. For example, for the dense layer or fully connected layer, for the M input and N output, we need to actually learn M times N parameters, and the complexity of our algorithm is big O of M times N. However, like in convolutional layer, we need to learn based on the kernel size that we have, where our kernel is much smaller than our input. Therefore, in total, we need to learn, in this situation, the complexity of our algorithm is k multiplied n. And also, in general, this is better because less parameter means less overfitting, and at the end, better generalization of algorithm. So far, you see this example for the like input size of 3 in 3. But in a reality, the input size or input data are in a very large scale. Okay, for example, a CT scan images, it has like a resolution is 500 in 512 with a depth of 600, or even images which you are taken by your cell phone. They are with a size of different size. For example, is 256 in 250. But now imagine we have a one colorful image with a size of 100 in 100. Suppose you would like to create one single feature map with the same padding. If we choose to do this operation with CNN and our filter size of the 5, then in total we will have 25 times because we have also colorful images and 3 input channel. Therefore, in total we need to learn 75 parameters. But for the dense layer, the numbers are quite different. Uh, our input layers has like 100 power 2. Then we have also 3 input channel, and also the next layer is like also 100 power 2. At the end we have 300 million parameter which they need to be learned. Well, this is only one example, and in practice, we do not try to replicate CNN architecture with dense network because of the like a physical limitation that we have, and also like a computational cost. Another property induced by CNN is equivariant representation. It means the object detection is invariant to change in illumination and change of position, but internal representation is equivariant to these changes. For example, in this figure, we have 5 input images, and the region of interest which we would like to detect is, for example, these 3 grayscale pixels that we have. And another side, assume we have a good filter and it's tuned very well, and our filter is able to actually detect the feature map that we want. Therefore, if we move our filter to the different position of these images, even if we change the position of this region of interest to somewhere else, still we are able to detect the region of interest correctly. Indeed, the filter does not care where is the location of region of interest, and it can find it anywhere in the picture. The property is called equivariant to translation, and we can say like a function of f(x) is equivariant to a function of g if f g of x is equal to g of fx. And another point is like similar to the dense layer, we have also nonlinearity here in feature map. Like in CNN also, we use activation function on all feature map entries to introduce the nonlinearity in the network. And ReLU activation function is also very popular here. Uh, this is because it reduces the danger of saturation gradient compared to other type of activation functions such as sigmoid. And as you also saw in previous lecture, we have also different variant of ReLU and like leaky ReLU is also something which is also popular, pure ReLU as well here for the CNN use case.